So we are at the final, kind of very close to the final sessions. We have Sam Yates showing us some use case for using SIMD instructions in your architecture. And I wanted to let you know there is a link in the web page of the course, CSCS, where you can click, and you get access to a folder, a Dropbox folder with the course material. If you can actually try it, that it works. I actually didn't try. I didn't run the test, as you know. I say you should test that all the time, but I don't have to do it. And maybe you have to refresh the page. Maybe I have to open the folder. It works? Okay, awesome. And there will be also then Anton's slides later on, and some other slides. So there will be more stuff later on. You can check that link. And I think we're good to go. So I'll let Sam do his presentation.
Thank you. Is this working? Oh my God, it is. Thank you. So ignorance knows no bounds. So I'm going to talk about vectorization. Why, or what it is, why it's good, what the compiler will do for us when it comes to vectorization and what it won't do, and how we can try and force the compiler's hands into vectorizing our code using explicit SIMD intrinsics. And then in the second half, the longer half of the talk, I'll go about how we might make a library that hides all the messy details from a user of SIMD instructions in a way that's hopefully also easy to extend and easy to maintain. And we get to see a couple of C++ patterns in the process. So let's start with some code. I'm going to also try out this thing. Oh, look at that. So on the left-hand side, we have a simple function. It gets two arrays, there's A and the B. It multiplies the first array by some scalar, adds a second array, stores it in a third array. And if we cast our minds back in time to the Pentium 3 era, which had no vectorization instructions, no SSE, this is the code that you'll get. This whole talk, in fact, owes a great debt to the Compiler Explorer, and this is directly from Compiler Explorer. And you can see here we don't need to know all the details, but we've got a kind of a mul and an add. We've got some sort of loop here, the L2, and we've got like a loop counter, this RAX, and it goes up 8 every time. If you do the division, you'll see that we have a loop. It goes 32,768 times doing one multiplication and one add. It's almost exactly like the code over here. Now, if we allow the compiler to make code for an actual modern architecture, on the right here, you'll see that there are a couple of big differences. The first one is that we have all these V's, and then all these V's turn up in the assembly code. And the other one is that we're adding 32 in the loop. So we're doing 4 times fewer iterations of this loop. And it's not like it's been unrolled. We've still got the one mul and the one add, whatever they might mean. So somehow these muls and adds are doing 4 times as much work. And that's because they are in fact SIMD instructions, single instruction, multiple data. They're actually doing a multiplication or an add on 4 values at the same time. So apart from the fact that a modern CPU is considerably faster than a Pentium 3, they're also doing 4 times as much work per instruction, which is huge. And it's one of the reasons why computers are so much faster. And the compiler did this for us, right? We didn't have to do anything. Before I continue, I just want to point out a couple of weird things. First up on the left-hand side, that restrict in red. Restrict isn't actually C++. It's not part of the standard. It is in the C standard, and many C++ compilers support it. All it means is that it's a promise to the compiler that things I get to via that pointer C, I won't be able to get to by other pointers. There'll be no aliasing. And that allows the compiler to make some assumptions about what it can get away with. It doesn't have to check that I've just overwritten A or B when I write to C. And so the code that we get is more compact and easier to understand. It's often actually what we want for speed as well. But the main reason I'm using that in these samples is to generate assembly code that's not too complicated, that we can all kind of follow. without much trouble. More of a concern on the right-hand side is this FP contract equals off. I didn't even know this flag existed until quite recently. GCC and the Intel C compiler also, when you ask them to do a high level of optimization, like -03, they'll take a multiply add, a combined multiply add like A times B plus C, and automatically turn it into a fused multiply add, an FMA. Now, an FMA operation does the multiply and add in one go, so it's faster, and it also is more accurate, so it sounds like a really good thing to do. But by virtue of being more accurate, it gives you different results. With an FMA, instead of a mul and add, we won't get the same output, typically, than we will with a mul and add. It doesn't preserve the semantics of the code. It's basically cheating. Maybe in a good way, but it's cheating. So to preserve the semantics when we're going through these various optimizations and assembly output, I'm going to tell G++, for example, not to do that unless I want it. So FP contract equals off says, don't muck around with my muls and adds, please.
Can I
Yep.
also add this restrict thing is put on C because this is where you're going to write into. Basically, restrict says that whatever access I'm doing here will be isolated from any other. So you could put restrict also on A and B, but since they are red, it's probably not an issue. So you probably get the same code. And one of the main complaints that a Fortran programmer has against C and C++ is the fact Fortran does not have this issue here, because in Fortran you instantiate multidimensional arrays and they will not overlap with one another. Here you can pass pointer C which overlap with A, or with B, or with both of them, basically the storage area. So the compiler has to be conservative and instantiate a code that does one operation at a time. So if you say C does not have any issue, then the compiler is free to do more stuff. And it's actually interesting that this restrict keyword is not in C++. It is brought up at every meeting, and people keep saying we don't need this one because the compiler can do a good job, but then you have to do this if you really want the compiler to do a good job.
I'm going to look at the stuff on the right-hand side in a bit more detail. I know that everyone here is very familiar with x86 output and SIMD instructions, but for my own sake, I'm just going to go through these. We've got these XMMs and YMMs and so on. These are the names of so-called vector registers on a modern x86 CPU. These days, there'll be 15 of them, 0 through 15. And the way it's written describes how it's going to be used. The XMMs mean I'm going to treat the register as 128 bits, the bottom 128 bits. The YMMs, if your processor has AVX, means I'm going to look at the 256 bits of the register. And finally, if you have AVX 512 extensions on your chip, we have ZMMs, where the registers are in fact 512 bits long, and ZMM means use the whole thing. So on the right here, we've got a V broadcast SD that takes something from a 128-bit register, puts it in a 256-bit register. What do the bits mean? Broadcast means I'm going to take a value and fill up all the vector lanes in my vector register. So if it can fit 4 doubles in there, then each double will have this value. And we know that the doubles, because there's that D on the end, the D stands for double precision. The S next to it means that it's going to operate on something with just one value. It's taking a scalar. Later on, we have this V mul PD. The P stands for packed, and that means it's going to operate as a vector. It's going to do the same operation. Well, it's going to incorporate all the things in the vector register. So that will help keep us aware of what the code is doing that we see on the right-hand side. So there we go. There's the code that GCC made for us. Now, if we go back, we see that we asked for Skylake, Skylake AVX 512. This is like a modern chip with AVX 512 registers, the whole 512 bits where you can fit 8 doubles. but it's only doing 4 doubles in the operations. Why is it only doing 4-wide vectorization? Just, who knows? If we ask Clang, it uses the whole register. It does 8 multiplications per multiply and add. It does 8 adds. It's doing twice as much work. It's a mystery. We don't know why Clang is doing this and GCC was doing only 4-wide. So that's one of the problems that we have. If we just allow the compiler to do what it wants, we don't have much control over it, and we can't really fathom its distinctions, why it chose one over the other. And in particular for GCC and the Intel-C compiler, when you use the high optimizations that you might want to get vectorized code, it might, even without us asking it, make changes in your code that will change the output. So I do want to point out, though, that these compilers are getting very, very clever. On the left-hand side here, we have another simple function. It takes the difference between 2 arrays and takes a dot product with the 3rd array, gives a scalar output. We run that through Clang, and, well, it's a bit of a mess, but you can see that these are all SDs. They're all scalar operations. It's an unrolled loop, but it's doing scalar operations. We're not getting any vectorization. But if we say, use fast math, fast math, then it does something quite clever. It unrolls the loop 4 times, uses these 8-wide vector operations. It combines the add and the multiply into a fused multiply add. It doesn't add up the values along the way. It stores them in 4 registers, ZMM0, 1, 2, 3, down on the bottom here. And at the end of the loop, it then reduces all these values that it calculated separately into a single value, which is the dot product. So this is a quite sophisticated transformation of the code that Clang did for us. All we had to do is ask Clang to do fast math. Fast math means, compiler, I don't really care about mathematics, just make it go. It pretends, for example, you don't have any infinities. It pretends that you never have not a number. It says it's okay to do operations in different orders. It allows you to fuse additions and multiplies. It basically says, pretend everything is finite and nice, and we don't actually live in a floating point computational land. And maybe that's fine. Maybe that's fine for your application. Many, many circumstances, it's not fine. You'll get different answers, and you'll have no error checking. Fast math is very often not what you want. But it's the only way to make Clang do these sorts of transformations. Another issue is transcendentals, and this is certainly something that came up often in our project. I've got a vector. I want to take the exponential of everything in it. And again, we ask Clang to do something with that. And, oops, wrong one. There we go. How did it go all the way there? Yeah? Oh, well, no, thank you. Clearly I do this all the time. I know what I'm doing.
Bi-directional
where are we? There we go. Sorry about that. So it's unrolled the loop. That's the dot product. Okay, exponential. Here we go. It's unrolled the loop, but it's doing a bunch of stores onto a stack, then pop things off the stack. If you look through it in a bit of detail, you'll find that it's calling this exp-finite routine with a single double every time. It's serialized it. It's calling one exponential after the other. So of course it's really slow. For all the use of these vector instructions, it's not actually vectorized. So that's a problem. If you want vectorization to work from your compiler, you may have to ask it to do fast math, which is an extremely loose way of doing computation in numerics. And even then, even if you say, do what you want with my mathematics, it still can't vectorize things like exp. And lastly, the other nail in the coffin is scatter conflicts. Now, scatters are something that's not often supported in hardware, but it is on the AVX512-based chips. And a scatter means I'm going to do a write, but I don't want to write the values from my array next to each other. I want to use an index. I want to say, first one goes here, second one goes over there, third one goes over there, and so on. Sort of an indirect indexed access. You can see that on the left-hand side, we're just going to write in index I of C the product. And Clang will actually do the right thing. We've got that scatter, which means use an index to write these values, and it's otherwise vectorized. That's fine. Then this case is not fine. What if we want to add it? And you look on the right-hand side, and you've got all these XMMs again, and the SDs, and it's all serialized. And we can even ask Clang, why did you not vectorize my code? And it tells us that there is an unsafe dependent memory operation in the loop. And this is because our indexes can overlap. Index 2 could be equal to index 4, meaning that I need to add 2 values to the same location in memory. And Clang said, look, I just don't know. I'm just going to serialize everything. Even if we know, for example, it never happens, we don't have any way to tell the compiler that that's never going to happen. So that's the other problem. We have no way within the standard language of saying, look, there aren't any conflicts. I can't use the standard equals operation to express that. So the alternative is to write the vectorization ourselves using so-called SIMD intrinsics. An intrinsic is not standard. It's sort of a built-in function provided by the compiler for a particular platform. They often reflect certain operations that are supported by the hardware, or they might give you things like branch hints or something like that. But the key thing is that they're very specific to an architecture and compiler. Compilers these days often support a bunch of SIMD intrinsics, which reflect the SIMD operations, these vector operations for a particular architecture. And luckily, they tend to be the same across compilers for the same architecture. Code that uses intrinsics from GCC will typically work with Clang and typically work with the Intel compiler. The Intel compiler is a few more because they like to be a bit special, but broadly speaking, they will work. But they don't actually mean I'm going to generate that exact instruction. You're asking the compiler to do what that instruction would do. And often, it will be that instruction, but not necessarily. The compiler is still free to elide loads or work things out at compile time if it can, or reorder instructions, that's fine. But it'll be semantically equivalent to doing the SIMD operation that it represents. Now, if we go back to our original example, well, nearly the original example, I'm using FMA here, just keep things simple. There's the vectorized code that we get for free. I can also write that with intrinsics. But set1 PD, that's like I'm going to fill the vector up with this constant. I've got this load, another load, fmadd, store u. It's a bit arcane, but these are the vector operations I've been asking the compiler to build into the code. And the generated code is exactly the same. I've just written the old code in a really hard to read way. But that will always be vectorized code if the compiler and architecture supports it. So SIMD instructions, intrinsics, they can be good. You'll get code that reflects what you actually write. The number of transformations and sorts of transformations the compiler will do will be very limited. You don't have to use fast math. If you want to write code that deals with not numbers and infinities, well, you can just pick the appropriate intrinsics. That's all good. If you don't have to. You can write your own transcendental functions. I could write a version of exp, for example, that uses vector operations all the way through, so I can do 4 exponentials at a time, which is a huge benefit. And I can be quite explicit about scatter conflicts. I will use the intrinsic which says do a scatter because I know that my values are independent, for example, my indices are independent. Now, the downside is that every architecture will have different intrinsics. If I want to use AVX2 instructions, I'll have a different set of these special functions than from AVX 512. If I want to use Neon on ARM, it would be completely different again. They're all idiosyncratic and they're all different. Even the order of operations can change between extensions. I think it's one of the scatter operations in AVX 512. Just has 2 of the arguments the other way around compared to AVX2, gather, I think. Great, thanks, Intel. So they're really hard to maintain. Also, they're really not standard. Compilers tomorrow might decide, oh, we're not going to do this anymore. Oh, okay. And the worst bit is that they're completely unreadable. Believe it or not, this does an absolute operation. I mean, it's obvious to me. No, that's terrible. Luckily, we have some alternatives. You can use OpenMP SIMD. I mean, you can use it. I can't because I don't understand it at all. I've never touched it, but it does exist. And that may be the solution for your problems with vectorization, and I'd recommend that you have a look at it. On the downside, while it is a standard from OpenMP, I think it came in OpenMP 4. It's not part of the C++ standard, so it's not standard in that sense. There's an excellent library, which I would recommend wholeheartedly, called VC. This is publicly available. It's open source. There's a link to GitHub. If you do want to use explicit vectorization, like we're going to be talking about in this talk, use this library. It is really good. In fact, it's so good that it has spawned a proposal for the C++ standard library, the parallel data extensions. It seems very likely that this will get incorporated, if not the next version of C++ and the version after. And you can just wait. You can just wait until this becomes part of the language. Or you could do what we did and write our own library, which is clearly crazy. The reason why we did this was that VC didn't actually do everything that we wanted, especially regarding transcendentals or indirect memory accesses. And we all really love writing numerical code that approximates transcendentals using rational polynomials because everyone loves doing that. That's just huge fun. Luckily, it also turned out to be a good example for a talk like this because it incorporates a number of C++ patterns. So what do we want to do? Well, what did we want to do? We wanted to broadly follow the proposal that's coming up in the C++ standard, mainly because it'll be easier to migrate to it when it finally gets incorporated. And also, a lot of hard work's already gone into designing this proposal, and we can just use that hard work in our API design. We don't have to reinvent everything from scratch. This is an example of code written against this proposed standard. And you can see there's no SIMD intrinsic in sight. That's all handled for us. We have a way of saying how big a vector of doubles should be, each iteration, a double for. We read them from memory. We say it's an aligned access. So we read in 4 doubles, read in another 4 doubles. Then our actual arithmetic looks like regular arithmetic. Just multiply by a constant, add another one, and then we write it to memory. And it turns out you can actually run this right now. The VC library has a...
Question. This element aligned, is it because you know that you have alignment in your data?
Yes, actually, I don't know that I have alignment in my data. I'm cheating. But yes. Okay. Sorry. We don't know here that double is actually aligned to the degree that the vector demands. I'm playing fast and loose, and it's a good call. Thank you. I'm going to throw it away anyway. We're not going to use that in our code, so. You can take this code, even with this error in it, and run it right now. If you go to the Compiler Explorer and cut and paste that code, but replace the experimental SIMD with a link to VC's version of the SIMD library, you can see what comes out, which is great. And what comes out is, in fact, just like our original one, a nice vectorized loop. Oops. I keep pressing the wrong button back. Here we go. Our next design criterion is that I want the Uservisible API, all these times and pluses, to be quite separate from the implementation behind the scenes for any particular architecture. And the main reason for this is that there's going to be a lot of syntactic sugar at the front end to make it all look pretty and easy to use. And I don't want to have to replicate that for every particular architecture. I want to do it once, and then use some sort of internal API that gets translated to that better reflects the sort of operations that go in any back-end implementation. So it saves effort, it makes things more maintainable, it encourages code reuse. And also means that if I want to change the front end, if I want to make a different way of presenting this functionality, I can leave the backends alone. As an example, and this is what our ultimate code is going to look like, I might have some way of doing a double for A, like a 4-wide vector with an addition and some sort of indirect memory access. And the backend code, what that gets translated to by our front end, will look something like the right-hand side, where I've got some concrete vector type A, and of course an add function, and then of course a scatter function, and so on. So our front end will basically be the mapping from the left-hand side to the right-hand side. The third criterion is that I don't want the functionality, like how to do an add, dependent upon the type used to represent 4 doubles or some sort of architecture-specific representation of the format. It's a separation between the operations on data and the representation of the data is not an object-oriented approach. Is there a name for this sort of principle? We can see it in a number of libraries where you separate your data from your operations. Anyone?
You can call it. You can call separation of concern, but also generic programming is what you're trying to do. For instance, in the STL, you have your containers, you have your algorithm, and you have a way for them to talk to each other.
I guess this is then an example of that desire. The main motivation for this is that the same representation of a vector, like a built-in vector type, may be used for different purposes. In one particular example in our library, we have the same representation type for 8 integers as we do for 4 long integers. There's no way to disambiguate based on the type of representation how to interpret that data or do the operations on it. So we're going to make a distinction. We're going to say that we have an implementation that provides functions that act on the corresponding representations. And lastly, and this is something very important for the development, I want to have some way of saying, I can't implement that particular function on this architecture, or I don't want to implement that particular function on this architecture yet. I want there to be some way of using a fallback that might be inefficient, but will work everywhere. And then I can just write the functions that I want to go fast on a particular system. And again, that also reduces a bunch of redundant code if I have to implement a fallback method for an unsupported operation on many architectures. I can just use the one. So let's work with that. Let's make a prototype library that does all these things. Just to keep the scope fairly limited, I'm going to make 2 backends. One for AVX2, the AVX2 instruction set extensions for x86, which deal with 256-bit vectors. And I'm going to use a generic one. And by generic, I mean this will work everywhere. I'm going to pretend that my vectors are standard arrays. It's just going to be standard C++ code. It's going to be slow, but the interface will be the same, meaning that I can write code that uses my library and will work everywhere. It'll just be fast, and I have AVX2. In terms of the arithmetic operations, I'm just going to do addition and multiplication and maybe FMA, and I'll only consider doubles and ints. We could, of course, expand this out to divisions and shorts and whatever, but we're just keeping it simple. We need some way of getting things in and out of these vectors, so I'm going to have some store to and from memory operations. I want to be able to get inside a vector. I want to get the third element of my vector. And because it was really pertinent to our design of our library in the first place, I want to implement these so-called indirect indexed operations, where I have an index vector, and I want to use that index to access things in memory, to read or write. And I'm going to start from the back end. The front end is fun, fluff, but the back end is where we have to get down and dirty with SIMD Intrinsics. So let's start there. In the proposal in the upcoming standard, there's a notion of an ABI tag. An ABI tag in the proposal says, if you're going to have a vectorized double for this tag, it's going to have this particular fixed binary representation, which is great. And you can use different ABI tags to get different, possibly incompatible representations. For our purposes, that's a bit general. We're going to nail it down a bit and cheat. And say that an ABI tag is something that maps a scalar type and a desired width of the vector to a particular implementation. So it is more specific than the standard. So my AVX2 is going to be a map. It's going to say, if you want a double that's 4 wide, tell me what my implementation is going to be, AVX, and it will give me that implementation. Similarly, generic will be an ABI tag. Say, I want a vector of 8 ints. Generic, give me the appropriate implementation that will provide that. And these are examples of type maps. A type map is really just a function on types. I'm going to have this convention, which loosely follows the proposal, that in our little namespace ABI tag, whatever that might be, takes two parameters, a scalar type and a width, and then the type field will give me the implementation class that represents all the work that we need to do on that sort of representation. ABI generic will always work. It will be something that will always return implementation that works with arrays. ABI AVX2 will only work for those that are supported by our AVX2 backend, which is quite limited, and otherwise be void. And with that in hand, we can write a default ABI type map, which says just pick the best you've got. Give me AVX2 if you've got it, otherwise give me the generic one. And that involves a bit of template metaprogramming. We didn't really cover this sort of thing in this course. You have to trust me that it's not too hard to write something like this, a first not void of. You give it a bunch of types, it returns the first type back that wasn't void. With that in hand, something like default ABI is quite simple. We just take the first that's not void of AVX2's version of it, or the generic version. If we had more backends, we could put an AVX 512 in there as well, or whatever we like. And then we have to now we've got our type map idea instead. What actually is an implementation? How are we going to represent that? We need two bits. We need to know what the data type is going to look like. We're going to have to use these things, and we need to have some way of describing the set of functions we can do on it. And as said before, we wanted functions separate from the representation. So one way to do that is representing the implementation by a class full of static members. Each static member is an operation. And then we have a traits class that will map an implementation to things that we need to know about it, such as the concrete representation it will be acting on, what the scalar type is, what its width is, and so on. The functions that we put in our big class of functions, our big bag of functions, correspond to the functionality that we decided we were going to support. These copies, the lane access, the element access, conversions from scalars to vectors, and arithmetic, and so on. Here's an example of our traits class. We can say that by default, everything's void. We just have no information. But if we have a concrete class, we can specialize it on it and give the information that we need to the rest of the ecosystem. So for AVX2 double, for example, double 4, which could be an implementation of 4 wide double in AVX2, we'll say that the traits will map to something. It says with the width of 4, the scalar type is a 32-bit int, and the vector type is this sort of internal type, underscore M256D, the details of which we don't have to care about. And this is our fallback implementation. Is this the right place to put that? I'm pressing the wrong button, aren't I? Here we go. Let me start that again. So there are our traits. A fallback class, and I also mentioned this at the beginning, is sort of a grab bag of implementations that will work everywhere so that we don't have to implement everything for every architecture. And all the fallback implementation needs, really, is a way of copying to and from the vector representation. Once it's done that, it can do everything serially with a for loop. It can be really, really basic. So every hardware implementation that we make has to support a copy to and copy from, and it has to have a traits class so we know what we're going to copy to and from into. And then it can leave everything else up to the fallback implementation, ideally, meaning we don't have to do any more work unless we want to make things fast. This is what our fallback class will look like. It needs to be parameterized because we need to know it's going to be different for every backend because I'll be on different types and different widths and have different vector representations. So that's why we have this parameter I. I stands for implementation, and because I hate typing, implementation. So I is our implementation class. And if we've got this stored to the copy to and copy from, we can implement everything else. The broadcast operation, which takes a scalar and fills out a vector. All we do is make an array of the right width, fill it up with our scalar, and say vector implementation, copy your values from my array. Similarly, add, we make a couple of vectors. I should point out store is just an array, whatever that might be. I'm going to read in the values into my arrays. I'm going to do the addition by hand, and then I'll ask the vector implementation to store that back in whatever vector type it has. So clearly, this is not vectorized code. If it gets vectorized, it's because the compiler is clever enough to do it. We're not doing anything. And we can do that for every piece of functionality we want to expose in sort of the backend interface. When we get to doing something concrete, like a 4 wide double vector, we've got the copy to and copy from. We need those. And again, we're using arcane SIMD intrinsics. We've got a specialized version of broadcast. We know how to do a broadcast quickly, so we'll use an intrinsic for that. And then I might say, oh, well, I'm feeling lazy. For add, I'm just going to use the fallback implementation. I'm not going to write my own. So we need to tell fallback which class to use, which is ourselves, AVX244. And if we were doing this for every piece of functionality, we'd have to have a wrapper around each one. We'd have one for add, one for mul, one for gather, one for scatter. Every piece of functionality would be duplicated with one of these wrapper functions. And we can avoid all that if we just, in fact, inherit from the fallback class. They'll just be there already. Which means we get this curious construction, and this has got a name. It's called the curiously recurring template pattern because it turns up all over the place in a curious manner. Here we're using it to provide default implementations. It's also used for something called static polymorphism, which I'm not going to go into in much detail. It's often abused. People come from other languages like Java, for example, where we've got interfaces and classes, and they want to do the same thing except with templates. And it turns out you can. It's just not necessarily a good idea. But for us, we're just using it to provide fallback implementations, default implementations. And the way it works is that the derived class, which for us is this AVX244, if it doesn't have an implementation, it will use the implementation from the parent, the fallback class. But the fallback implementation has to use the derived class to work out how to do things like copy. And for more sophisticated functionality, like exponential, it may use things like, how do I do an add quickly, or how do I multiply quickly? So the missing methods are automatically provided, but the base class has to use facilities in the derived class to do what it does. And this is why we've got this weird circular sort of dependency. It turns out it's not actually circular. The fallback class here is just a class. It doesn't contain an AVX244. It doesn't have to know much about it. It's still curious, though. Now, there are problems with using CRTP. If you're used to standard inheritance in C++ and virtual functions, the compiler will help you. If you use virtual and override and you make a mistake, the compiler will say, hey, you tried to override something that's not virtual, or this hides that other thing that is virtual, and you probably didn't mean that. It holds your hand a bit. With this technique, there's no help. There's no analog of override. So if you make a mistake, and it's very easy to make a mistake, I might use add instead of I::add in the fallback class. The compiler will just accept it. Now, with various macros and testing, you can make a framework for making sure that you don't make this sort of error, but it's quite involved. The compiler will not help you. So that does increase the maintenance burden a bit because of the ease of making a mistake. Now, just for completeness, because we haven't talked about CRTP in this course, I want to show you how it works when you're not just using static functions. You can do it for regular classes as well. And the idea there is that if you want to call a method in the most derived class, you have to cast this pointer down to that class to get access to them. One use case for this is I'm going to present an interface to a user, which is implemented in our base class, which uses some low-level functionality I don't want to expose in my derived classes. And there might be a bunch of these there. They're all different. And again, the way we do it is our top-level function foo, that's very public. It will call these methods, whatever they might be, in the derived class. And all this thing does is do a static cast to the class D. We know that's going to work because we set it up that way. Our derived classes derive from base, parameterized on derived. And you can see that doesn't have a foo function. All the foos are supplied by the top class. When you're using it, you're using things of type derived, and the foos you get for free. But we're not doing that. I won't talk about it more, but you will see this turn up from time to time, and it's good to know what it is, so you can look it up on Wikipedia. It's CRTP. So let's get back to our design. For the generic implementation that was just going to use standard array, we can just use the fallback. I mean, it's not going to be vectorized anyway. We just need a way of copying to and from, and then we're done. we say that the vector type is standard array. Our copy to is just a copy. Our copy from is also just a copy. Our traits class is true for every t and n. The scalar type is t. Vector type is array. That's it. That's complete implementation of the generic one. But there's a lot of copies going on. If you actually use this in a function, if n is 1, the auto-vectorization from the compiler may do a good job. If n is greater than 1, it gets a bit confused. It's just a mess. But then our generic implementation is really there so that we can have an interface that will work everywhere, not necessarily be fast. Now, with all that said, does it actually work? Can I use this back in implementation with AVX2 to get vectorized code? And I wouldn't have made the slide unless the answer was yes, it does. And the answer is yes, it does. It does work. This interface is still kind of clunky, right? I've got these particular types. I've got these weird copy froms and FMAs. But it's not using SIMD intrinsics. They're all hidden from us. And the generated code is indeed just like the generated code we had before. It's a vectorized FMA. So we're on the right track. This sort of approach does work. There is one other thing I hadn't talked about yet, which are these scatters and gathers. They're a bit weird because they involve two vectors. There's the vector of values that we're pulling in from memory or pushing out to memory, and a vector of indices. And the values might be of type double, or a vector of double. Indices may be of type int, say, and they're heterogeneous operations. And as I said before, we may have different sorts of semantics associated with the same vector representation. So if I'm the back end, I'm given a gather operation to do, and I'm given the index vector, I need to know more than just that it is an index vector to work out how to interpret it. I need to know the right interpretation as well. I need to pass information to myself, the gather, that says this is actually an AVX2 int4 vector, not some other sort of vector, even though the representation as a type may be the same. One way to do this, and the way I would recommend, is to use a tag type. A tag is just an empty struct which carries type information. So a tag int is a different type from a tag double, even though they're all empty. And the good thing about a tag type is that I can have a tag for an incomplete type. I can declare a class without having done the implementation yet, and still talk about the tag parameterized on that class, which is useful in our case because this thing with indices mean that my AVX2 double may want to talk about the AVX2 int representation and vice versa. It can get very convoluted. Tags just sort of break that down. You're promising that when you need it, it'll be there. This is actually a use case that came up for us. AVX512 int 8 in our own library's implementation uses the same type as a long 8. So we need some way of saying, treat this as an int or treat this as a long, and we can do that with tag types. We just pass it as a parameter. We never use the value, we're just using it for its type. It adds it to the overload set. In the fallback, we use the type to know how to read values from the indices into an array, which we then just do serially. In the back end, we say, if it's this particular sort of index, then I can use the magic SIMD instruction that does the right thing. One thing to be aware of is this using fallback AVX344 gather. I'm saying pull into the class scope, all the versions of gather that are defined in the base class. If I don't do that, this overload here isn't an overload. It just replaces all the gathers, and things will break. This is a way of saying I'm going to take all my base class ones and also add this one. It's the same sort of thing for scatter. Well, here's a demo. It doesn't really matter that we go into the details. It's all a bit messy because this is still in the back-end code. But it's enough to know that it works. And finally, we can get to the fun stuff, which is the front end, how we make this pretty and easy to use for people. The way we're going to represent this is we're going to have a wrapper around an implementation class called SIMD wrap, because I like creative names. And it will contain a single piece of data, which is the representation type for the implementation. I'm going to expose this to users via another type map, the SIMD BN ABI. So remember, ABI itself was a template class. So using a using declaration, I can say that if you ask for a double 8 from AVX2, I'm going to give you back the SIMD wrap of the type that AVX288 gave me. And for the indirect stuff, the sort of gather and scatter information, I'm going to make an indirect expression and a nice little wrapper function called indirect that represents that in memory. And then I can overload on that in my implementations. So let's get started. What does SIMD wrap look like? We want a constructor, obviously. A copy constructor is default. For a scalar, we're going to use that broadcast functionality. For copying values from memory, we're going to use copy from, and so on and so forth. And this is very straightforward, but just providing an interface to the backend that we already have in this class I. Similarly, the operator equals acts like our constructors. We use a broadcast if we're going to assign a scalar, return ourselves, and so on and so forth. So they're very straightforward. Arithmetic, well, we want to be able to do things like A plus B being translated to the backend's add operation. And again, we're going to use things in the library. Again, we're using the friend trick that you saw earlier to make sure that these are going to be found by ADL. It's a function rather than a method. It takes two SIMD wraps, calls the backend add thing, and this little wrap function is just there to make our lives easier. It creates a SIMD wrap object with that value. And again, if we add more arithmetic operations, we add more corresponding ones to the wrapper, just like so. Element access, we get to use a proxy, slightly exotic. It's fine if we just want to get a value out of an array. We can use operator braces and say, well, backend, just give me the element at that position. But if I want to use it on the left-hand side, I need to be able to remember what my index was and how to do the operation. So much like something like Vectorization, when we ask for an operator, like a bracket expression, when it's not const, I'm going to return an element proxy. The element proxy remembers what I'm talking about and where it is. And when we finally get around to assigning it, it will call setElement. And lastly, the indirect operations. This is something which is not in the proposal. This is something that we did because we thought it was a good idea. I still think it's a good idea. And that is, rather than having gather and scatter and these very particular terms, we'll just say do what you need to access memory via this index. And an indirect expression will represent that. Here, for example, we have a gather operation. I want to say let V be the SIMD vector type that corresponds to the values in memory starting from P using indices, whatever indices might be. And if I just swap the left and the right-hand side, now I've got a scatter operation. We probably won't have time to look at the sort of compounding add problem that gave us a problem at the beginning of this talk, but we can also use indirect for that as well. So the indirect expression needs to keep track, again, of the important pieces of information, the pointer and the indices that are going to be used to indirect through that pointer. And then we overload the equality operation, assignment operation, here to do the actual copy to. The copy to is provided by the wrapper object that we were talking about before, and we're going to have to overload that too, so it can copy to an indirect expression, not just a pointer in memory. And it's, again, a delegation. We say that when we do a copy to with indirect, we're going to call the scatter function. The indirect expression already has the type of the index representation, so we can use that directly to set the right tag, so the right version of scatter is called. And that's pretty much our infrastructure. We're done. That's our whole library. The original example that we came up with was this scalar multiply and then add another array example, this SMA. CI is K times AI plus BI. In our vectorized code, I left out a big N. You have to assume that N is defined to be 32768. I left that out of the example. It's just a big number, there's power of 2. I'm going to load VA from memory, VB from memory, do the operation, and then copy to C in memory. And it's quite similar to the version of the code we had that uses the experimental C++ interface, except we're lazy and we don't have the element aligned stuff. Our implementation just presumes it's unaligned and plays it safe. And again, the generated code we have on the right-hand side is vectorized. It did the right thing. For indirect operations with gathers, again, we can just use this new indirect expression to say, take the 4 doubles at this indirect address indexed by index at A, and these from B, multiply them together and copy them to C. And sure enough, on the right-hand side, we get the AVX2 gather instructions, and it's all vectorized. So again, we found a way of expressing our SIMD intent with a syntax which isn't too horrible. Now, we didn't do a couple of things that are really important for a SIMD implementation. One is masked expressions and conditionals. I want to be able to conditionally assign values in my vector or conditionally do an operation based on some test. It's not that hard to write. We need a different sort of wrapper that supports logical operations. Our SIMD wrap supports sort of arithmetic operations. But a mask object, again, will be a wrapper around an implementation, just like the ones we already have, but it'll provide a different interface. It'll provide bitwise operations and ANDs and so on. And these will be what we get when we do a comparison. We'll overload our comparison operators to give us one of these mask wrappers instead of a regular wrapper. A where expression, much like our indirect expression, will be like sort of a placeholder that when it turns up in an arithmetic expression or in an assignment operator, there'll be an overload that will unpack it and then actually do the back-end masked operations as required. Another missing feature is conversion and casting. If I've got some float values in a vector and I want to turn them into double values in a vector, I should be able to do that. And we can. This is another example of a heterogeneous operation. We have 2 different types, vector types that we have to deal with. And much like gather and scatter, we can solve the problem with tag classes. We have a cast from method in our implementation classes that takes a tag and then does all the work. Now, I haven't done this for our tiny SIMD language, SIMD library. The example code won't have these 2 things in it, although the version in our project does. I was just going to leave them out. Now, that's basically the end of the talk. There's some good resources to look at. First up is the example code. All this stuff that I've been talking about lives in a tiny repo. It may not quite yet be on our sources, but it will be soon. It does a little bit more than what I discussed. It also talks about constrained indices and compound scatters, which I'll get to if we have time. I think we don't have time. The compiler intrinsics that are used to provide the backend, at least for Intel, can be found here, the Intrinsics guide. There are literally hundreds, if not thousands of these, and if it weren't for the guide, I think we would all be lost. If you want to know what the operations the SIMD intrinsics are wrapping, Felix Cloutier's website is excellent as a full reference. And if you want to know how expensive they are, Agnifog's instruction tables have tables of latencies and throughput is also extremely valuable. And lastly, as you saw through all these examples, the compiler explorer is a godsend if you're trying to do this sort of work. I cannot recommend this site highly enough. And there we are. Are there any questions?
So the tiny SIMD library is in the repository now. I didn't see your pull request.
Just as information, at the beginning I saw that you use O3.
Yes.
Did you test with OFAST or you never use it?
I tend not to use it, but there's no reason why I couldn't. We can try it.
I don't know, because it's not recommended. It's unsafe to use it, so I don't know if you encountered some behavior, maybe interesting.
Yeah, I would say let's try it out. Let's go to the compiler explorer and give it a go. But I guess I'm used to using O3, so that tends to be what I use. I think OFAST does things like fast math, which is almost never what I want.
Sure.
So for example,
Sure.
so yeah.
And with O2, well, it reduces the size of the program, but that doesn't mean it will use less. Well, it could use less instruction.
Well, to be honest, if it weren't for the fact that O3 with some compilers does non-semantic preserving transformations, I would say there's no reason to use anything other than O3 or OS for minimizing size unless you're time constrained or you want to look at debug output. So many things in modern C++ require the compiler to work out that all these abstractions don't actually mean anything and can produce tight code. That using O2 is sort of putting one hand behind your back and trying to compile. So I would normally recommend O3.
Sorry, that's just a curiosity. Do you use this library at CSCS for all the projects? Do you plan to do that?
So currently we're just using it for our one project, our project. And one of the reasons for that is that we've only implemented the bits that we need. A fully useful solution would require supporting more scalar types. For example, we don't have any unsigned arithmetic in our library because we don't need it. Well, that's basically it. And more support for more transcendental functions and the like. This would be work that is worthwhile. There is some talk about making this a more fully featured library and available for general use. But on the other hand, almost everything that you would use our library for, you could just use VC for instead, which is a much more mature project. As I said, there were some reasons why we're doing our own thing, but they probably don't apply to many projects. So I'd recommend using VC instead.
What would be the required changes to your SIMD to support transcendentals?
Sorry, I didn't quite hear you clearly.
What would be the required changes to your library to support transcendentals also? Like the way we were showing before, support for SIMD's transcendental computations.
Sorry.
Exponent for
Transcendental.
Transcendental. Sorry, I just didn't hear you clearly. Yep. Sorry about that. So what we do in our current library for transcendentals is that for each transcendental, we have something in the implementation that does a rational polynomial approximation with some munching to handle the exponential side of things. So we do some special handling using LDExp, for example, to extract the exponent from a double, and then do a rational poly approximation. What VC does is it uses a generic way of doing this. It implements an LDExp function for its vectors, and then it uses that, plus mask expressions to catch NAND cases and infinities and the like, to provide an implementation that works for all their vectors. We don't actually do that. We have specialized implementations for AVX512 and AVX2. And one of the reasons for that is that, well, with AVX512, we can use the LDExp that's supplied by the architecture, which handles NANDs all by itself. It's easy to write a fully featured exponential. But we don't have that facility with AVX2. We have to do some bit tricks to do the equivalent of an LDExp. And so we have to do more work. We have to treat the NAND case separately, when we don't have to in the 512 case. So we do things differently just to get that little bit of extra performance out of it. And that's because exponentials turn up a lot in the code that we're using.
I have a question. So FMAs are more accurate because they use the 80 bits expansion internally.
Well, that could be how they do it, but practically the operation as defined is to do the combined operation with exact rounding. Okay. So whatever the chip has to do.
So vector instructions do not do that, I think, right? They will just do the basic, they will not, basically they will not use the 80 bits expansions or other specific tricks that FMA will use. You will get
not since AVX2. I think at least with Intel chips, all the ones that actually support a built-in FMA instruction do a correctly rounded FMA following the IEEE spec. Okay. Even in AVX2, actually, the first version of it didn't have an FMA. It's like the next version of AVX2 had an FMA, but I believe it's a correct FMA.
Okay, so my next question is, so you're implementing your transcendental functions,
mm-hmm.
and you said at the beginning, well, no, we want to control the order in which the user wants to control the order in which instructions happens. But then, if you implement your own transcendental functions, how is your user trusting you that you're doing a good job?
Well, they have to trust us at some point. What we do with our exponentials, because they are rational polynomial approximations that aren't correct to the last bit, they're correct to the last 1 or 2 bits, but they're going to be the same across all of our vector implementations, and that's what we ensure. So if we use any one of the vector optimized ones, even in the generic case, you'll get the same answer as if you use a different one. And that's our repeatability guarantee.
So just a practical question for your examples. You need to import submodules. How do you do that with Git?
Git submodule, I'll write it up. That should do the trick. Now, I don't know how we are on time, and I don't know if there's any interest, but I can talk about our constrained indexes and how we solved the problem of the plus equals update, but I won't unless there's some interest in this.
But you have a question, I guess.
Yeah, just out of curiosity, why do you care about this reproducible output to the last bit in your project?
It's mainly to catch other errors. If we're reproducible across different compiler options, well, different compilers and different platforms, and we know that we're supposed to be reproducible, and then we see a different answer, then we know we've got a problem somewhere in our workflow or somewhere in our code. It reduces one potential problem. Ultimately, the numerics that we do should be robust to these small changes. They shouldn't matter, and they don't matter in terms of the output from an experimental or a simulation point of view. But they do help immensely in a sort of maintenance and bug finding point of view.
Just make a comment. I think that things like this, are driven by real cases, the real things that you have to do, right? And then you have to think how to deal with your space. You have a space in terms of design constraints that you have. You have to support different compilers. You have to support different architecture. And you want to keep the user code same. So all these kind of constraints will lead you to develop solutions that reach your goal. So you might have a better library out there, like this VC library. It might be too general, it might be difficult, it might be maybe a user don't want to have an external dependency, they want everything in there. So there's a lot of consideration, and at some point you would say, well, it's time for me to really solve these things for good, or for at least for some time. And so yeah, this is just one example. Say that basically I think everyone in our unit has done something like that. They had a problem. They decided, okay, we need to design one interface that helps us to basically get rid of these things. So we solve it, we keep using it, and we don't have to think about this anymore. Or we have to extend it maybe, but we have something that actually is a tool for us. That was muted. You didn't hear anything.
We heard it in our hearts.
Yeah. So now, I don't know. You interested in who's interested in seeing this index implementation? Nora, yeah. And
I've got 2 people.
Okay. Two people.
2 people. It's happening. Sorry, guys. Right.
2 people are enough.
Yeah, 3. Okay. So I wasn't going to go into the same sort of detail. I just wanted to show how we solved this problem, how you might solve a similar sort of problem. And that problem was that when we're dealing with indirect memory accesses through indices, without doing something special, there's no way of saying we know more about these indices than you might just by looking at the array, and thus the compiler can't make a good decision. So gather and scatter is typically slow. If we knew all the indices in our particular vector were the same, we could just load a scalar, we'd be done. If we knew that all the indices were next to each other, like 2, 3, 4, 5, we could just do a regular load. So with a bit of information, we can use faster methods to get the data. So what we're going to do in our library is add a so-called constraint. And this is knowledge that we're telling the library about our indices. There's a promise about our indices. We've made a bunch of them. They form a little dependency tree. Constant means they're all the same. Contiguous means they're like in order next to each other. Independent, I'm guaranteeing that I'm not going to have two things hitting the same location. Monotonic, actually in our case just increasing. And none, like a free-for-all, that's like the default case. I'm not making any guarantees about my indices. And we can add that to our indirect expression. We already have an indirect expression. We can add a constraint to it too. It will default to none, or default to, I don't know. But once we've got that, we can dispatch on that constraint to better versions of a gather or a scatter or indirect load or a plus equals operation. That's basically it. You can look at the source code if you are interested. That's in the repository. And there's a little demonstration there, a little benchmark that indicates that in some circumstances, for example, where I've got lots of writes into a small vector, but they're ordered, where many of the indices are going to be the same, we can do much better than an unconstrained write. There's another example in there where we guarantee that all the writes are sparse and independent, and it turns out not to be any faster. And that's mainly because the AVX2 instruction set doesn't support a scatter operation at all. The vectorization we get doesn't account for enough to make a difference. In our own project, the Arbor project, this has proved to be a huge boon, and this is in fact Nora's work in the implementation of that in our library, and improved, I think, performance on AVX2 and AVX 512 by a factor of 2, ultimately. So, and 4 times is amazing, right? So these do have practical application. That's it.
So at the beginning of your presentation, not this short one, but the other one, the big one. So you showed the implementation. One was with 228 registers, and the other one with 256 registers, right? So GNU was giving you the X registers, and Clang was giving you the Z.
That's right.
Sorry, GC was giving the Y, and Clang was giving the Z. Do you see performance impact on this, or is this particular benchmark just bandwidth bound and you don't care much?
To be honest, in this particular benchmark, I don't know. I was going to run this on Alt, but Alt's been down for maintenance. I didn't have access to it. So I can't tell you. I imagine that it will, in fact, be faster, just on the grounds that you are literally doing less work. But you may only see that if our kernel is sufficiently complicated, and maybe not in this case. The other aspect, of course, is that if you're using, I know you know this, but just for general information, on modern Intel chips, if you're in AVX 512 mode and using AVX 512 instructions, the whole core will slow down. It can't actually do the work at full frequency. It just gets too hot. So unless you actually are getting enough benefit from your vector operations that you're not bandwidth bound, you'll actually run slower. There's not always a clear-cut choice to use AVX 512 instructions over, say, AVX2 instructions.
Yes, it's not clear, right? This vectorization thing, especially if you're running in a bandwidth-bound case, you're basically bound from loading data from the RAM, and so the vectorization might help a little bit, but it might be like small.
If you're sitting in nearest cache, more great. If you're not, then yeah.
Any other questions? Okay, so let's thank Sam.